MapReduce.
MapReduce is a programming model for processing large datasets with a parallel, distributed algorithm on a cluster. A MapReduce program is composed of a map procedure that performs filtering and sorting, such as sorting students by first name into queues, one queue for each name, and a reduce procedure that performs a summary operation, such as counting the number of students in each queue, yielding name frequencies. The MapReduce system, also called infrastructure, or framework, orchestrates by marshalling the distributed servers, running the various tasks in parallel, managing all communications and data transfers between the various parts of the system, and providing for redundancy and fault tolerance. The model is inspired by the map and reduce functions commonly used in functional programming, although their purpose in the MapReduce framework is not the same as in their original forms. The key contributions of the MapReduce framework are not the actual map and reduce functions, but the scalability and fault tolerance achieved for a variety of applications by optimizing the execution engine once. As such, a single-threaded implementation of MapReduce will usually not be faster than a traditional implementation. Only when the optimized distributed shuffle operation, which reduces network communication cost, and fault tolerance features of the MapReduce framework come into play, is the use of this model beneficial. MapReduce libraries have been written in many programming languages, with different levels of optimization. A popular open-source implementation is Apache Hadoop. The name MapReduce originally referred to the proprietary Google technology but has since been genericized.
Overview.
MapReduce is a framework for processing parallelizable problems across huge data sets using a large number of computers, nodes, collectively referred to as a cluster, if all nodes are on the same local network and use similar hardware, or a grid, if the nodes are shared across geographically and administratively distributed systems, and use more heterogeneous hardware. Computational processing can occur on data stored either in a file system, unstructured, or in a database, structured. MapReduce can take advantage of locality of data, processing it on or near the storage assets in order to reduce the distance over which it must be transmitted. Map step: the master node takes the input, divides it into smaller sub-problems, and distributes them to worker nodes. A worker node may do this again in turn, leading to a multi-level tree structure. The worker node processes the smaller problem, and passes the answer back to its master node. Reduce step: the master node then collects the answers to all the sub-problems and combines them in some way to form the output, the answer to the problem it was originally trying to solve. MapReduce allows for distributed processing of the map and reduction operations. Provided that each mapping operation is independent of the others, all maps can be performed in parallel, though in practice this is limited by the number of independent data sources and/or the number of CPUs near each source. Similarly, a set of reducers can perform the reduction phase, provided that all outputs of the map operation that share the same key are presented to the same reducer at the same time, or that the reduction function is associative. While this process can often appear inefficient compared to algorithms that are more sequential, MapReduce can be applied to significantly larger data sets than commodity servers can handle. A large server farm can use MapReduce to sort a petabyte of data in only a few hours. The parallelism also offers some possibility of recovering from partial failure of servers or storage during the operation. If one mapper or reducer fails, the work can be rescheduled, assuming the input data is still available. Another way to look at MapReduce is as a 5-step parallel and distributed computation. Prepare the map input. The MapReduce system designates map processors, assigns the K1 input key value each processor would work on, and provides that processor with all the input data associated with that key value. Run the user-provided map code. Map is run exactly once for each K1 key value, generating output organized by key values K2. Shuffle the map output to the reduce processors. The MapReduce system designates reduce processors, assigns the K2 key value each processor should work on, and provides that processor with all the map-generated data associated with that key value. Run the user-provided reduce code. Reduce is run exactly once for each K2 key value produced by the map step. Produce the final output. The MapReduce system collects all the reduce output, and sorts it by K2 to produce the final outcome. Logically, these 5 steps can be thought of as running in sequence. Each step starts only after the previous step is completed, though in practice they can be interleaved, as long as the final result is not affected. In many situations, the input data might already be distributed, sharded among many different servers, in which case step 1 could sometimes be greatly simplified by assigning map servers that would process the locally present input data. Similarly, step 3 could sometimes be sped up by assigning reduce processes that are as close as possible to the map-generated data they need to process.
Logical view.
The map and reduce functions of MapReduce are both defined with respect to data structured in key value pairs. Map takes one pair of data with a type in one data domain, and returns a list of pairs in a different domain. Map K1, V1, list, K2, V2. The map function is applied in parallel to every pair in the input dataset. This produces a list of pairs for each call. After that, the MapReduce framework collects all pairs with the same key from all lists and groups them together, creating one group for each key. The reduce function is then applied in parallel to each group, which in turn produces a collection of values in the same domain. Reduce, K2, list, V2 list, V3. Each reduce call typically produces either one value V3 or an empty return, though one call is allowed to return more than one value. The returns of all calls are collected as the desired result list. Thus the MapReduce framework transforms a list of key value pairs into a list of values. This behavior is different from the typical functional programming map and reduce combination, which accepts a list of arbitrary values and returns one single value that combines all the values returned by map. It is necessary but not sufficient to have implementations of the map and reduce abstractions in order to implement MapReduce. Distributed implementations of MapReduce require a means of connecting the processes performing the map and reduce phases. This may be a distributed file system. Other options are possible, such as direct streaming from mappers to reducers, or for the mapping processes to serve up their results to reducers that query them.
Examples.
The prototypical MapReduce example counts the appearance of each word in a set of documents. Here, each document is split into words, and each word is counted by the map function, using the word as the result key. The framework puts together all the pairs with the same key and feeds them to the same call to reduce. Thus, this function just needs to sum all of its input values to find the total appearances of that word. As another example, imagine that for a database of 1.1 billion people, one would like to compute the average number of social contacts a person has according to age. In SQL, such a query could be expressed as: using MapReduce, the K1 key values could be the integers 1 through 1100, each representing a batch of 1 million records. The K2 key value could be a person's age in years, and this computation could be achieved using the following functions. The MapReduce system would line up the 1100 map processors, and would provide each with its corresponding 1 million input records. The map step would produce 1.1 billion, Y-N-1 records, with Y values ranging between, say, 8 and 103. The MapReduce system would then line up the 96 reduce processes by performing shuffling operation of the key value pairs due to the fact that we need average per age, and provide each with its millions of corresponding input records. The reduce step would result in the much reduced set of only 96 output records, Y-A, which would be put in the final result file, sorted by Y. The count info in the record is important if the processing is reduced more than one time. If we did not add the count of the records, the computed average would be wrong. For example, if we reduce files number 1 and number 2, we will have a new file with an average of 9 contacts for a 10-year-old person. 9 plus 9 plus 9 plus 9 plus 9, /5. If we reduce it with file number 3, we lose the count of how many records we've already seen, so we end up with an average of 9.5 contacts for a 10-year-old person. 9 plus 10 closing round bracket over 2, which is wrong. The correct answer is 9.179 plus 9 plus 9 plus 9 plus 9 plus 10/6.
Data flow.
The frozen part of the MapReduce framework is a large distributed sort. The hotspots, which the application defines, are an input reader, a map function, a partition function, a compare function, a reduce function, an output writer.
Input reader.
The input reader divides the inputs into appropriate size splits, in practice typically 16 megabytes to 128 megabytes, and the framework assigns one split to each map function. The input reader reads data from stable storage, typically a distributed file system, and generates key-value pairs. A common example will read a directory full of text files and return each line as a record.
Map function.
The map function takes a series of key-value pairs, processes each, and generates 0 or more output key-value pairs. The input and output types of the map can be, and often are, different from each other. If the application is doing a word count, the map function would break the line into words and output a key-value pair for each word. Each output pair would contain the word as the key and the number of instances of that word in the line as the value.
Partition function.
Each map function outputs is allocated to a particular reducer by the application's partition function for sharding purposes. The partition function is given the key and the number of reducers and returns the index of the desired reducer. A typical default is to hash the key and use the hash value modulo the number of reducers. It is important to pick a partition function that gives an approximately uniform distribution of data per shard for load balancing purposes, otherwise the MapReduce operation can be held up waiting for slow reducers assigned more than their share of data, to finish. Between the map and reduce stages, the data is shuffled, parallel sorted/exchanged between nodes, in order to move the data from the map node that produced it to the shard in which it will be reduced. The shuffle can sometimes take longer than the computation time depending on network bandwidth, CPU speeds, data produced and time taken by map and reduce computations.
Comparison function.
The input for each reduce is pulled from the machine where the map ran and sorted using the application's comparison function.
Reduce function.
The framework calls the application's reduce function once for each unique key in the sorted order. The reduce can iterate through the values that are associated with that key and produce 0 or more outputs. In the word count example, the reduce function takes the input values, sums them and generates a single output of the word and the final sum.
Output writer.
The output writer writes the output of the reduce to the stable storage, usually a distributed file system.
Performance considerations.
MapReduce programs are not guaranteed to be fast. The main benefit of this programming model is to exploit the optimized shuffle operation of the platform, and only having to write the map and reduce parts of the program. In practice, the author of a MapReduce program however has to nevertheless take the shuffle step into consideration. In particular, the partition function and the amount of data written by the map function can have a large impact on the performance. Additional modules such as the combiner function can help to reduce the amount of data written to disk, and transmitted over the network. When designing a MapReduce algorithm, the author needs to choose a good trade-off between the computation and the communication costs. Communication cost often dominates the computation cost, and many MapReduce implementations are designed to write all communication to distributed storage for crash recovery. For processes that complete fast, and where the data fits into main memory of a single machine or a small cluster, using a MapReduce framework usually is not effective, since these frameworks are designed to recover from the loss of whole nodes during the computation. They write interim results to distributed storage. This crash recovery is expensive, and only pays off when the computation involves many computers and a long runtime of the computation. A task that completes in seconds can just be restarted in the case of an error. And the likelihood of at least one machine failing grows quickly with the cluster size. On such problems, implementations keeping all data in memory and simply restarting a computation on node failures, or, when the data is small enough, non-distributed solutions will often be faster than a MapReduce system.
Distribution and reliability.
MapReduce achieves reliability by parceling out a number of operations on the set of data to each node in the network. Each node is expected to report back periodically with completed work and status updates. If a node falls silent for longer than that interval, the master node, similar to the master server in the Google file system, records the node as dead and sends out the node's assigned work to other nodes. Individual operations use atomic operations for naming file outputs as a check to ensure that there are not parallel conflicting threads running. When files are renamed, it is possible to also copy them to another name in addition to the name of the task, allowing for side effects. The reduce operations operate much the same way. Because of their inferior properties with regard to parallel operations, the master node attempts to schedule reduce operations on the same node, or in the same rack as the node holding the data being operated on. This property is desirable as it conserves bandwidth across the backbone network of the data center. Implementations are not necessarily highly reliable. For example, in older versions of Hadoop the name node was a single point of failure for the distributed file system. Later versions of Hadoop have high availability with an active-passive failover for the name node.
Uses.
MapReduce is useful in a wide range of applications, including distributed pattern-based searching, distributed sorting, web link graph reversal, term vector per host, web access log stats, inverted index construction, document clustering, machine learning, and statistical machine translation. Moreover, the MapReduce model has been adapted to several computing environments like multi-core and many-core systems, desktop grids, volunteer computing environments, dynamic cloud environments, and mobile environments. At Google, MapReduce was used to completely regenerate Google's index of the World Wide Web. It replaced the old ad hoc programs that updated the index and ran the various analyses. MapReduce's stable inputs and outputs are usually stored in a distributed file system. The transient data is usually stored on local disk and fetched remotely by the reducers.
Criticism. Lack of novelty.
David DeWitt and Michael Stonebreaker, computer scientists specializing in parallel databases and shared nothing architectures, have been critical of the breadth of problems that MapReduce can be used for. They called its interface too low-level and questioned whether it really represents the paradigm shift its proponents have claimed it is. They challenged the MapReduce proponents' claims of novelty, citing Teradata as an example of prior art that has existed for over 2 decades. They also compared MapReduce programmers to codicil programmers, noting both are writing in a low-level language performing low-level record manipulation. MapReduce's use of input files and lack of schema support prevents the performance improvement enabled by common database system features such as B-trees and hash partitioning, though projects such as Pig, or Pig Latin, Sawzall, Apache Hive, Ismart, HBase and Bigtable are addressing some of these problems. Greg Jorgensen wrote an article rejecting these views. Jorgensen asserts that DeWitt and Stonebreaker's entire analysis is groundless as MapReduce was never designed nor intended to be used as a database. DeWitt and Stonebreaker have subsequently published a detailed benchmark study in 2009 comparing performance of Hadoop's MapReduce and DBMS approaches on several specific problems. They concluded that relational databases offer real advantages for many kinds of data use, especially on complex processing or where the data is used across an enterprise, but that MapReduce may be easier for users to adopt for simple or one-time processing tasks. Google has been granted a patent on MapReduce. However, There have been claims that this patent should not have been granted because MapReduce is too similar to existing products. For example, MapReduce functionality can be very easily implemented in Oracle's PL/SQL database-oriented language or is transparently for developers supported in distributed database architectures such as ClusterPoint XML database or MongoDB database.
Restricted programming framework.
MapReduce tasks must be written as acyclic data flow programs, that is a stateless mapper followed by a stateless reducer, that are executed by a batch job scheduler. This paradigm makes repeated querying of data sets difficult and imposes limitations that are felt in fields such as machine learning, where iterative algorithms that revisit a single working set multiple times are the norm.
Conferences and users groups.
The first international workshop on MapReduce and its applications, MapReduce 10, was held in June 2010 with the HPDC conference and OGF 29 meeting in Chicago, Illinois. MapReduce users groups